Launching in 3, 2, 1.
Holy.
This is my cannon. It's very large, and it fires these projectiles to several hundred feet. In my recent videos, I built and tested a scale version of the spin launch concept, which uses a giant spinning arm to boost a rocket into the air. This is a really cool idea, but what if instead of a big arm, I just used a cannon? Unsurprisingly, this is not a new idea. In the 1950s and 60s, the US and Canada funded something called Project HARP. The whole Project HARP history is really interesting, and the channel Real Engineering did a really good in-depth video. I'll leave a link below. But this absolute unit of a cannon had like a 180-foot barrel and could fire almost a 200-pound projectile over 100 miles into the air. That's basically halfway to the International Space Station, which is crazy. This is such an interesting idea that I really want to replicate it on a small scale. So here's the plan. I'm basically going to start off by just building a giant potato cannon to fire a projectile as high as possible. And then I'm going to use this tiny camera to film what it would look like if you were on board the rocket as it was shot out of the cannon, which should make for some pretty incredible footage. Before I started building the cannon itself, I needed a good base. So I broke down some plywood into the size I needed, and then I framed up some 2x4s for underneath it to support everything. Now to make transporting this thing easier, I designed everything to fit into a truck bed. So this base is 4 feet by about 5 feet. I framed this kind of like you would a house, I guess, but then I had some extra wood, so I just added it in between the joist. This should hopefully make everything even more rigid. The plywood just gets held on with some screws, and by some screws I mean a lot of screws. I must have drilled like 100 holes in this thing. And then of course no project is complete without a little bit of paint. So I just rolled that on, and this is honestly just interior paint, so we'll see how well it holds up being outside. But as of now, I haven't seen any issues yet. This air cannon is actually made up of 2 different parts, the air tank and then the valve and barrel. The air tank is just built out of 4-inch PVC pipe, and this is just normal PVC pipe that I got from my hardware store. I cut down all the lengths I needed just using a chop saw, which was really quick and easy, but the PVC dust the saw makes is very statically charged, which makes a huge mess. It sticks to everything. All these sections I cut get glued together with connectors. Now something I realized while I was doing this was that a lot of the connectors sold at like Home Depot are not actually rated for pressure when you get into the 3-inch and 4-inch sizes. They're mostly meant for drain lines, so they're only rated to like 5 PSI, or sometimes they're not even rated for any pressure. So I had to order Schedule 40 fittings, which are actually not that much more expensive, they're just hard to find. All of these get glued together using this primer and glue combo. The primer is the purple stuff, which is supposed to clean the surface, and then the glue has a solvent in it that actually melts the plastic together when you put the pipe into the fitting. Gluing PVC together like this is so satisfying because it's super quick, but it is permanent, so be careful. I definitely made some sort of measurement error halfway through this, and so some of the pipes were longer than I needed, so I trimmed those down, and then everything fit together. Now to prevent measuring errors like this, I should have been referring to the 3D model I made in Onshape, which is also the sponsor of this video. Onshape is a cloud-native CAD software which runs in your browser, so you can use it anywhere. You can even use their app to pull up models and reference dimensions on the go. This is really helpful, and it could have prevented an easy measuring mistake like this. Onshape has all the features of a fully fledged CAD program, with the capability to do detailed models and assemblies. With the cloud-based models, Onshape makes version control extremely easy, and it allows you to fork designs and roll revisions sort of like GitHub. It can do all of this without needing to save any clunky files. And because everything is stored in the cloud, all of your updates are always saved. This means if your computer has a problem or if there's a power outage, you don't lose any work, which has saved me multiple times. I've been using Onshape as my CAD program of choice for a couple years now, and I have not looked back. They even have features like the ability to do structural simulations, a CAM studio, and the ability to create drawings, all of which have come in handy on past projects. The best part is that it's free for hobbyists. So try out Onshape for your next project using the link in the description below. The base of this is 4 feet by 5 feet, so this thing is giant and heavy. So I need a way to aim it accurately. And to do that, I'm putting a trailer jack on each corner of the platform. This will allow me to independently change the height and aim the cannon one way or the other. I use my CNC router to cut out some of these triangle pieces, which are sort of braces for the corner. These just get attached with some screws, and then the trailer jacks slide into those braces. The trailer jacks get held down with some leg bolts, which should be more than strong enough for this. The valve that actually releases the air tank is this 2-inch ball valve. It's pneumatically actuated using this really cool rack and pinion system, and I was actually pleasantly surprised with how fast it was. In 3, 2, 1. That thing is fast. I think this might actually work. With air cannons like this, how fast you can release the air is really important. It's honestly more important than the air pressure itself. The first valve to trigger is this tiny solenoid valve, and this actually triggers a 1-inch sprinkler valve. This 1-inch valve allows a lot more flow than the small valve, and this triggers the big ball valve. So basically I'm using 2 valves to control another valve, which might be a little counterintuitive, but I'm hoping this makes it actuate as fast as possible. I also have a couple manual ball valves on here, and that's so I can vent some air and manually return the ball valve to the closed position when I'm loading the cannon. On the other end of the ball valve from the air tank is the barrel. And interestingly enough, the fittings I had the hardest time finding were getting from a 2-inch thread to a 4-inch sweat fitting for PVC. So I kind of had to make do with what I had, and so I actually 3D printed a coupler. To do this, I used the Formlabs Tough 2000 resin, which is kind of like an ABS material, and this stuff is extremely tough, as the name implies. After the part was printed, I put it through a wash cycle to get all the extra resin off. And then I removed the support structure, which is extremely satisfying. These support structures on resin parts always look so cool. The supports did leave little bumps on the part, but that's fine because we can sand that off later. This resin does require post-curing, but after that was done, I smoothed everything out with some sandpaper, and then used some epoxy to join everything together. Since I'm not using PVC glue for this, I did make sure to rough up all of the PVC fittings with some sandpaper, just to make sure I get a really good bond. This is definitely not a use that this resin was intended for, but it should only be pressurized for a split second when it's launching the projectile, so hopefully it handles it just fine. With all the valves done, the only thing really left on this is the electronics, and they're pretty simple for this project. I'm controlling everything with an RC transmitter, and then I'm using a relay to turn on and off an air compressor, and a MOSFET for firing the valve. I also added this analog pressure sensor just to give me an idea of how high the pressure is in the cannon. It's definitely a little overkill for this project, but I did use my PCB breakout boards for this. This board is a design I came up with where most of it is just a perf board that you can mount anything you want to on, so you still have a ton of flexibility, but it has a spot where you can easily mount a microcontroller, and then it automatically breaks out the ground and all the voltage lines to a bunch of easy to use pads. It avoids having to solder like 5 wires to the same pin on the microcontroller, which I have done countless times. If you're interested in these and you think you might be useful for one of your projects, I do have a link in the description below where you can pick one up. With all the electronics packed into this nice waterproof container, this whole cannon is ready to be tested. For the initial projectiles, I designed this sort of rocket-looking shape. The base of the rockets is printed out of orange PETG on the Prusa Core 1. They sent this over to me a couple months ago, and so far I've been very happy with it. But for some reason, the base of these rockets, I had 2 failed prints. Oh no. Absolute mess. So this was a little bit of a bummer. It was most likely a little bit of user error, but in the end, the final parts turned out really good. Now these rockets currently don't have a parachute, so they need a very durable nose cone. So I decided the best idea was just to test a bunch of materials. So I printed nose cones out of PLA, PETG, TPU, resin, and carbon fiber nylon. As soon as I got a free weekend, I went out to the testing field to fire this thing off. Since this thing is so big and heavy, I ended up adding wheels and a hitch to it so I could pull it with the tractor. This thing weighs at least a couple 100 pounds, so this made life way easier. A little bit of lubrication never hurt anybody. After getting the cannon out to the field, I used the trailer jacks to position everything correctly. To tell me which direction the cannon was pointed, I used this digital angle finder, which was really handy, considering the ground's not even close to flat in this field. All right, first step here is to assemble the barrel. This is an 8-foot long barrel. I don't know if that's too long or not long enough, but I figured it's a good starting point. So, I also printed this muzzle brake. Look at this thing, it's awesome. Honestly, one of the bigger prints I've probably done. Slides right on there. And I'm not even gonna glue it, I'm just gonna let it stay on there with friction. Hopefully that's fine. Ugh. I feel like it really brings the look of this cannon to where it should be. Now, we just gotta load up the barrel. For the projectiles I'm using, it's this. Now, if you grew up in the early 2000s, this might look familiar to you, and that's because I got the idea from this, which is a Nerf Vortex. I feel like everyone played with these things as kids, and the best part about it is you could feel like you could just throw it like a mile. They absolutely soar. This one's got a cool like whistle tip on it too. Those things are awesome. So I basically have a tiny 3D printed version of it, and this is what we're gonna fire out of it, and we'll see how far it goes. The other thing I'm interested to know is what of these nose cones is gonna protect the rocket enough that when it lands, it doesn't just shatter. I don't have parachutes in these, so we're gonna test out a couple different materials. First up is just normal old PLA. If I just put this into the barrel, a lot of air would scoot around it as it goes out the barrel, so I printed these, which are called sabos. And these actually are used on normal like tank projectiles as well, but they just clamshell on either side, and they make this the same diameter as the barrel. It also looks really cool, look at that. So, take this. I'll be honest, the muzzle brake makes it a little hard to load, but it looks cool, and that's what matters. It makes it very hard to load. After trying to load this thing for probably 5 minutes, I realized there was an even bigger problem. The print down here is actually a little too small. It's like the projectile can just barely fit through there. Somehow in the process of designing this muzzle brake, I made the inner bore too small at the base. And this would probably be catastrophic if we tried to fire it this way. So after a little bit of a struggle getting the muzzle brake off, I can fix it using a little bit of redneck engineering. I didn't have anything to grind down the PLA, so I literally just heated up this pipe with a blowtorch and then melted the plastic to make the diameter larger. It's definitely not the most elegant solution, but it did work. Perfect fit. Then, take my stick here and just push it all the way down. Very satisfying noise. All right, this goes back on here. Goes back, screws right into here. I still can't believe how large it is. 8 feet might have been a little much on the barrel, but that's all right. We're gonna test it out. Now, before we launch it, I do this thing angled down the field by about 4 degrees. The wind's coming this way today, so hopefully that means it will go that way, because we don't want it going this way. That's where the tractor is. Don't hit the tractor. That'd be very, very bad. So we're gonna go that direction, and then hopefully that's enough of an angle to take care of the wind trying to blow it back this direction. So let's give it a shot. Using the TNT microcontroller on board the cannon, I was able to read the analog pressure transducer and then send those measurements as telemetry data over the ELRS protocol back to my radio transmitter. This is the first time I've used this feature of ELRS, and it was really handy for knowing what pressure the tank was at. All right, we're at 81 PSI. Launching in 3, 2, 1.
Holy.
Oh, thing went way up there. It's also coming down. You hear that howl it made? That was aggressive. That was also so loud.
I was scared.
All right, we definitely need to angle it a little bit more, but that was pretty awesome. All right, well, it looks like everything survived. Nothing exploded except for the sabot. The sabot, which used to look like this, now is in about 100 pieces and got absolutely shredded. We'll have to look at the slow-mo to see what happens there. But the bigger question is, did the rocket survive? Because I wanted to put a camera in the rocket, but if it's just going to get destroyed, then I need to build a stronger rocket or put a parachute in there. So it's over there in that wood somewhere, so let's go find it. I see it right over there. I can see some little orange plastic bits sticking up. Oh yeah. Wow. Crazy enough, even just the PLA nose cone survived. The actual rocket tube itself broke in half, probably just from the force of it coming to a stop. But the actual rocket kind of survived. I think a camera probably would have been fine in there. So now all we gotta do is increase the pressure and put more stuff inside here. All right, to keep it from going into the woods again, I'm gonna angle it maybe a degree that direction. So get it up to, perfect. And then I'm gonna angle it another 2 degrees downrange because that one came a little too close. Now, unfortunately, to reload it, I need to pull the barrel off. Then to think about how hard it'll be to get up inside there. So let's unscrew this. I'm really impressed that this resin piece survived. It's literally just a printed coupler because I couldn't find the part I needed at the store. All right, so for the next launch, I'm not gonna put the camera in yet, but I do have this altimeter, which is just based on barometric pressure. So it should give us an idea of how high these go. And for this one, I'm gonna use the TPU nose cone. So we'll see if it survives. All right, let's load it up. Going vertical. There we go. Currently at 30 PSI. All right, seems like it's kind of plateauing around 83 PSI right now. So we're gonna go ahead and fire it off. Turn the compressor off. All right, 3, 2, 1. Holy cow.
As soon as I heard this one, I knew something went wrong. Now looking back at the slow-mo is a little difficult because the sabot breaks into like 10 different pieces, which makes it difficult to know what's going on. But one of the angles, if you play it back frame by frame, you can see that when the rocket came out of the barrel, the nose cone had already separated from the rocket body. For all of this stuff to break inside the barrel, there must have been a lot going on. And all of that, plus the less aerodynamic shape, made the rocket unstable, so it did not go very high.
Well, that wasn't good. I don't know what happened there. That was really loud though. Also, I saw the nose cone fly off, so that is not good. All right, let's go check it out. So here's the base. This is broken off, so that's a little bit of a clue. And then the altimeter, stuck in the ground. So miraculously it survived. It says 256 feet.
Since there were clearly some problems with that launch, I wanted to try it again with the exact same setup with just a different rocket and a different nose cone.
All right, I'm just gonna electrical tape this in place because anything with electrical tape is gonna work fine, obviously. This is the PETG nose cone. If PLA worked, I'm hoping all these should work. Well, I guess the TPU one clearly didn't work. I think my attachment scheme is also a little bit weaker than it probably should be. We're at 50 PSI and climbing. Get it up to like 80 again, and then we'll see what happens. Alrighty, here we go. We're at 80 PSI. 3, 2, 1. Oh yeah, that went way up there. Holy cow. There it is. Wow, that was aggressive. It looks like it made it in one piece, so let's go check it out. If you really zoom in, you can see the tail of it. We actually hit like dead center of the field, which is pretty impressive. Means we got the angles just right. 144 yards to that. All right, well, let's go see if it's in one piece. All right, here we are. The thing is buried. Oh, look at that. Oh, there was so much force when it hit the ground that the part that holds the electronics inside like came through the nose cone. That's crazy. Guess how high it went?
700 feet.
814 feet. That's pretty crazy. All right, well, I say we put a camera in it, see what happens. Camera's in there. Use a little electrical tape. What could possibly go wrong? Now this one, to hopefully protect this camera, is the carbon fiber nylon nose cone. So hopefully this one should be the strongest and protect the camera the most. So we'll hit record. And off she goes. Bye. Good luck. Alrighty, couple more PSI. All right, here we go. See if we lose the camera here. Firing in 3, 2, 1. Oh, it's a beautiful shot. There it is. Might hit the woods. Hopefully it made it. All right, moment of truth. You can see the tail sticking up. At least that all made it in one piece, so hopefully the camera's in one piece as well. Oh yeah, I think it's fine. The piece that was holding the camera definitely broke. Oh, look at that, still flashing red.
This camera survived quite an impact, and I was pleasantly surprised with how good the footage was. I was really happy with these initial results from the Canon, but there's a couple issues I want to fix in my next video on this. First off, when the projectile gets launched out of the barrel, you can see it's sort of unstable and wags back and forth. The projectile is moving really fast at this point, so it creates a ton of drag and limits the overall height that it reaches. So I gotta fix that. And part of that will also be fixing the sabos so they don't blow apart into a million pieces every time. They should just peel off in flight, and honestly I should be able to reuse them. Lastly, I think it'd be really cool to add a rocket motor into this, and maybe a parachute recovery system. But I'll save those for the next video on this.
All right, well, this thing worked fantastic. And we got some really, really cool onboard footage. Thank you guys for watching. Let me know if you have any ideas on what else I should do with this, and I'll see you in the next one.